Hi, this is Alex from devstories.eu. OpenCV Computer Vision Deep Dive, Episode 12 of 20. Running a heavy neural network on every single frame of a high-resolution video is computationally wasteful. Smart systems detect an object once and then use lightning-fast physics equations to predict where it will move next. This is the domain of persistent perception, object tracking algorithms. Picture a smart city traffic monitoring system. You need to count unique vehicles passing through a busy intersection. An object detection model looks at a single frozen moment in time. If you run pure detection on a video at 30 frames per second, a car stalled at a red light for 10 seconds generates 300 separate, disconnected bounding boxes. Without tracking logic, your system counts 300 cars. Detection finds the object. Tracking mathematically associates that object with its past self across time. To fix the traffic camera, you need a multi-object tracker to maintain a persistent ID for every vehicle. Modern trackers, like those implemented using RoboFlow and OpenCV, break this problem into two distinct mathematical phases. The first phase is prediction, and the second phase is association. When a car enters the camera feed, the initial detector draws a bounding box. The tracker extracts the center coordinates, width, and height of that box and assigns it a unique integer like ID 42. When the next video frame arrives, the tracker does not immediately scan the image. Instead, it uses a mathematical model, typically a Kalman filter, to perform state estimation. By evaluating how ID 42 moved over previous frames, the filter calculates the vehicle's velocity. It then projects those physical properties forward to predict exactly where the bounding box for ID 42 should be in the new frame. Now you have two sets of data for the current frame. You have the predicted boxes generated by the state estimator and the actual boxes just found by the detector. Here is the key insight. The tracker must reconcile these two sets to keep the IDs consistent without analyzing the actual pixels again. It builds a matrix comparing every predicted box against every newly detected box. The primary metric used for this comparison is intersection over union, or IOU. This measures how much the predicted geometric area overlaps with the detected geometric area. If the predicted location for ID 42 overlaps heavily with a newly detected bounding box, the system concludes they are the same vehicle. An optimization method, typically the Hungarian algorithm, solves this matrix to find the most logical one-to-one pairings across the entire intersection. The new detection inherits ID 42, and the tracker updates its velocity model with the new confirmed coordinates. This prediction and association loop inherently handles temporary visual obstructions. If a bus blocks the view of our car for a few frames, the detector fails to find it. However, the state estimator keeps predicting the car's movement behind the bus based on its last known trajectory. The ID is kept alive in a pending state. When the car emerges and the detector flags a bounding box that aligns with the tracker's ongoing blind prediction, the ID is instantly relinked. By bridging the gap between independent frames, multi-object tracking transforms a stream of static images into a cohesive map of moving entities. Tracking allows your application to stop asking what is in the frame and start understanding how things behave over time. That is all for this one. Thanks for listening, and keep building.